All right, this is the recording for chapter 9. I made my mouse cursor humongous. It's awesome. You can see it. It's pretty cool. I'm going to close my screen recording thing there. Hopefully it's still screen recording. Let's check. It is still screen recording. That's good. I'll just leave it there. It's not really in the way. Okay, so today we're in chapter... Wait a second. This is... chapter 10. That's right. Rotational motion and angular momentum. And they got this great picture, which is extremely, I mean, it just makes so much sense in Nebraska. It's very pertinent, I suppose. But anyway, a nice tornado there. It's not that big a one, but still, tornadoes are tornadoes. And the reason that tornadoes form is actually has to do with, of course, rotational motion. We know that. But it's actually, a big part of it is the angular momentum. There's angular momentum that is created by the storm, and as that cloud reaches down towards the ground, or as the wind starts to pull things up from the ground, is really what's going on. The angular momentum is conserved, but since it's such a small spout, in order to conserve angular momentum, you end up with extremely high speeds. Of course, tornadoes can reach speeds of hundreds of miles per hour. Of wind velocity around and around and around. So some cool stuff there. Anybody that's ever interested in storm chasing, you have to learn some physics. Anybody that studies storms at all is essentially they're earning a physics minor, and then they're specializing in storms. So looks like we have 7 sections here, from angular acceleration all the way through to gyroscopic effects. Excuse me. So, lots of fun stuff for us today. Another great example of this, and a classic physics example that physicists love, are the ice skaters. The ice skaters that do all their spins and everything. And I personally prefer to talk about angular momentum and rotational motion in sports like volleyball, where it is also very important. But we'll talk about the ice skater since we have the picture here. Of course, everyone has seen when an ice skater goes into a spin like this, their body is opened up here, and it's opened up because her head and her arms are way out here, her leg is way out here, and she could even open it up further by sticking her leg out, sticking her arms out, and then of course when they pull everything in tighter, they go faster. I don't know if she can pull in any tighter here, but she could certainly pull in tighter if she was standing with her leg down and pulled her arms in close and her feet in close. We've all seen that when they get going really fast. We're going to learn why that is the case here in this chapter. So let's talk about angular acceleration. We've already talked about angular velocity, which is this omega equals delta theta over delta t. So we're familiar with that, and we also know that the linear velocity, or the tangential velocity along the edge of the circle, the speed along the edge of the circle, as we call it, is equal to r times omega. We also know that we also should mention that omega can have a vector quality to it as well, just like the torque. When it's a clockwise angular velocity, we usually consider it positive. When it's counterclockwise, we usually consider it, sorry, the other way around. When it's counterclockwise, you usually consider it positive. When it's clockwise, we usually consider it negative. If we go ahead, though, and solve for omega here, excuse me, we get omega equals that tangential speed, or the speed along the edge of the circle, divided by r. And we have two different tangential velocities. They're different in direction, although they're the same in magnitude along the edge of the circle as the circle rotates through an angle theta with a radius r. And then to calculate, or to define the angular acceleration, which we're going to use alpha, that's not a little a, that's an alpha, the first letter of the Greek alphabet. We use delta omega over delta t, which is change in angular velocity over change in time, just like the linear velocity was defined, except in angular terms. And then, once we do that, we can actually plug in, and they do this down here somewhere, we can actually plug in v over r for the angular velocity and use that. It looks like they won't use it right away. So let's actually go to the next page and see if they do. Come on, next page. There we go. So here is where they do that. Since the angular velocity, well, they actually don't really do that here. What they're doing here is they're comparing the tangential acceleration with the angular acceleration and solving for tangential acceleration, which happens to be r times alpha. There's another equation here that will fit in. I guess they're saving it for later. That's okay. We'll go back to these examples and do them really quick. Okay, so we have 10.1, calculating the angular acceleration now from the deceleration of a bike wheel. They start the wheel spinning, and they find an angular velocity of 250 RPM in 5 seconds. Well, it spins from rest to a final angular velocity of 250 RPM in 5 seconds. They want us to calculate the angular acceleration in radians per second. We're going to have to do some conversion, of course, because they gave us RPM, which is rotations per minute. We'll have to convert that to radians per second. And then part B, she slams on the brake, and they have a deceleration of an angular deceleration that they give us, and they want us to know how long it's going to take. So converting our angular speed from 250 RPM is going to take a few things here. That's what we're doing right here. Delta omega is 250 revolutions per minute, RPM, times 2 pi radians per revolution, times 1 minute every 60 seconds. And that gives us 26.2 radians per second of delta omega, because we started from 0. And then the angular acceleration is defined as delta omega over delta t. And we get 26 radians per second, which we just calculated over the 5 seconds, becomes 5.24 radians per second squared for the angular acceleration. For part B, we rearrange the equation for the angular acceleration so that we get delta t equals delta omega over angular acceleration. And they've told us the angular acceleration is negative 87.3 radians per second squared. That goes in the bottom. And our delta omega is going to be from the, from the first part where we got the delta omega. That tells us the final speed in radians per second, and that's going to be our initial speed here, where our final speed is 0. So if we take final minus initial for this part, we get negative 26.2 radians per second, because it's slowing down. You get negative 26.2 over negative 87.3, and you get 0.3 seconds for this thing to stop. So, moving on now to talk about tangential acceleration. Tangential acceleration is how fast something is speeding up along the edge of the circle, and it is a tangential vector that will change constantly as whatever it is on the edge of the circle is going around and around it. But as we plug things in that we know, for example, we know that tangential acceleration is equal to the change in speed over the change in time along the edge of the circle. The change in speed along the edge of the circle is r times omega, and then we pull out the r because it doesn't change, only the omega changes, and we get tangential acceleration equals r times alpha, because alpha is delta omega over delta t. And this also tells us that the alpha is going to equal the tangential acceleration over r, or angular acceleration and tangential acceleration are related to each other by this equation. So we can use that now in an example. Example 10.2. We have a powerful motorcycle accelerating from 0 to 30 meters per second in 4.2 seconds. That's actually not a very powerful motorcycle. But what is the angular acceleration of its 0.320 meter radius wheel? So they've given us the radius. They've given us something about the acceleration. Now, how fast the motorcycle accelerates is actually equal to the tangential acceleration of the wheels, as long as the wheels don't slip. They really should say that the wheels don't slip here. And so you have tangential acceleration right here, 30 meters per second. And if you take the 0 to 30 meters per second and divide it by the seconds, you should be able to get tangential acceleration. And that's exactly what we're going to do. We're going to actually resolve this equation, alpha equals at over r, for the tangential acceleration a sub t. We get a sub t is then equal to a sub t is then equal to r times alpha, which they write somewhere around here, I'm sure. But anyway, we can calculate the a two different ways, though. We can calculate it here linearly by taking the 30 meters per second over 4.2 seconds. So we get 7.14 meters per second squared for the tangential acceleration. Then we plug it into this equation, it's divided by the radius of the wheels, and we get 22.3 radians per second squared of angular acceleration, which is nice. Now, we have dealt with we've dealt with linear displacement, linear velocity, and linear acceleration. Those were x, v, and a. And now we have rotational equivalents in in theta, omega, and alpha. And the relationship between the two as well. And it's always an r. To get the angular relationship, you take the linear relationship. To get the angular number, you take the linear number divided by the radius around something around which it's rotating, and you will be good to go. It's a very simple relationship, actually, once you get that understood. So, what this means is that we can also have kinematics for rotational motion. Oh, goody! You thought you were done with kinematics forever, but not really. We're going to make you do it in rotational stuff too. But the good thing is that you're not memorizing anything really new. You're just going to transfer your knowledge from linear kinematics into rotational kinematics, knowing that the relationships are pretty simple from that previous table. So here they're actually going to derive these kinematic equations for you, these rotational kinematic equations. They start with one of the simplest linear kinematic equations, final velocity equals initial velocity plus acceleration times time, and then they make substitutions. Since the linear velocity is equal to r times angular velocity, they just plug that in here and they plug it in here, and linear acceleration is equal to r times angular acceleration, they plug that in here, and when they discover that they have an r in every single term, they divide by r to simplify, and they get this equation, which should look very similar to the original one. And we have linear velocity, angular velocity final. Linear velocity initial, angular velocity initial. Linear acceleration times time, angular acceleration times time. Right? Here this looks like they have an a in there, and they actually do. That's a mistake. It should actually be a alpha like it is up here, alpha. And this one should say constant alpha, not constant a. That was a mistake on their part. But it is omega equals omega naught plus alpha times t. And you can do it with every single one of them, and it always turns out the same. For the rotational kinematic equations, you just replace x's with thetas, and v's with omegas, and t's stay the same. And a's with the a's and the linear a acceleration, you replace them with alphas. And you get all the rotational kinematic equations, and you're good to go. So it's no big deal, except that kinematics is always a pain in the butt. So anyway, here they throw on some other kinematic equations you can use if you want to. And of course, problem-solving strategy for rotational kinematics is essentially the same as it is for linear kinematics, except that you probably should convert everything into rotational things. So tangential velocities, which are linear velocities along a rotational path or a circular path, you should convert those into angular velocities. And you can convert things into angular accelerations and angular displacements. And then you can just plug them into the angular kinematic equations. So we're going to do one of these. We're going to calculate the acceleration of a fishing reel. A deep-sea fisherman hooks a big fish, swims away from the boat, pulling the fishing line from his fish reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.5 centimeters from its axis of rotation. So we have r. R is 4.5 centimeters. Convert that to meters. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds, as seen in figure 10.8. Where's figure 10.8? Let's find that. It's figure 10.8. So it's given an acceleration. Okay, we can accept that. It's given an angular acceleration, so they've given us an alpha, 110 radians per second squared. They've also given us a delta t, 2 seconds. They want to know what is the final angular velocity of the reel. They want to know what speed the fishing line is leaving the reel. Remember that something that is traveling along the edge of the circle, even if it leaves the circle, like the road or something like that, or the fishing line in this case, this speed would be a tangential speed. So we're looking for tangential speed in part B. How many revolutions does the reel make? Well, that of course we can find from figuring out how much angle in radians the reel turns and then dividing that by 2 pi for each revolution. And then how many meters of fishing line come off the reel in this time. And that would be, of course, a tangential distance, x, which we can also calculate. So part A, let's start with this equation that gives us the final angular velocity equals the initial angular velocity plus the angular acceleration times time. We know that the initial angular velocity is 0, starts from rest, so we plug in these numbers and we get final angular velocity is equal to 220 radians per second. So now we know the speed, the angular speed, we can calculate to the tangential speed, which is the speed of the line coming off the reel, because the reel was traveling on the path of that reel. So V equals R times omega. We have R, we have omega, we just calculated, we get 9.9 meters per second. Okay, that's pretty dang fast. Must be deep sea fishing. And then in part C, we're finding the number of revolutions. Well, the number of revolutions is going to be how much rotation it goes through. For rotation, we look at theta, and we can use this kinematic equation. Theta equals theta initial, which is 0, so they don't even put it there, plus omega initial times t, or angular velocity initial times t, plus 1/2 angular acceleration times t squared. Once they use that equation, and we have all that information, we get 220 radians that it rotates through. So it rotates through 220 radians. Well, how many revolutions is that? There's 1 revolution for every 2 pi radians, so you divide by 2 pi and you get 35 revolutions. On to part D. We want to know how many meters of fishing line are going to be released. Well, the meters of fishing line, or the distance, the tangential distance, is going to be related to the tangential the rotational angle that the thing rotates through, theta, times the radius. That's another one of the relationships that connects the linear x with the rotational theta. So we take the radius 0.045 meters, multiply by the 22 radians that it rotates through, and you get 9.9 meters of released line. So pretty simple stuff, because we've already done all this before. You just have to remember which one correlates with which one. The theta correlates with x, or distance and angle correlate, and then velocities correlate and accelerations correlate. This time we're going to calculate duration, fishing reels slowing down and stops, in other words how long it takes. So a fisherman applies a brake to a spinning reel, angular acceleration negative 300 radians per second. How long does it take the reel to come to a stop? We want to know the time. So we know that it's spinning. We don't know how fast it's spinning. Oh, I guess we're using the same fishing reel as the previous one. So the initial initial angular speed, or angular velocity, is 220 radians per second. The final will be 0 because we want to bring it to a stop. The angular acceleration, negative 300 radians per second squared. And we just have a simple calculation using this first kinematic equation. Plug in the numbers that we know, solve for t, you get 0.733 seconds. No big deal. Calculating slow acceleration of trains and wheels, also very fitting for the North Platte area and other places in Nebraska. Large freight trains accelerate very slowly. We have a 0.350 meter radius wheel, angular acceleration of 0.250 radians per second. After the wheels have made 200 revolutions, no slipping, we want to know how far the train has moved down the track. What are the final angular velocity of the wheels and the linear velocity of the train? So, essentially in part A, we want to know a tangential distance, or a linear distance. So that's going to be related to linear. It's going to be related to angular distance or angular angle, right? Rotation angle. So that's going to be a theta and an r and an x that are going to be needed for that. We're going to be calculating the x from r and theta. And then the final angular velocity of the wheels and the linear velocity of the train, well, we'll use a kinematic equation for that. So theta equals x over r, or x equals r theta. That's a relationship you should remember for all of them, because it's the same for the distance and angle as it is for the two velocities and the two accelerations. We're going to solve this one for theta, leave it solved for theta equals x over r, because we actually know, no, actually we don't know x, sorry. We're actually calculating x. But it doesn't really matter which one we're going to do, because we already know theta, so we can calculate x. Well, theta is given in revolutions, 200 revolutions. It goes around 200 times. And there are 2 pi radians per revolution, so we make that conversion into radians. You can't use revolutions in these kinematic equations. You have to use radians. And once we know the 1257 radians, then we can plug it into our equation up here. X equals r times theta, because we know the r. So r times 1257 radians is 440 meters down the track. You know, that's like 6 football fields, 5 football fields. Anyway, now we know how far it's gone, and we also want to know, what was the other thing we wanted to know? I can't remember. We want to find omega, angular velocity, angular and tangential velocity of the train. So we have to use an equation that has things that we know. What do we know so far? Well, we know how much angle it's gone through. We know the angular acceleration. That should be enough. So we use this equation here that has things that we know and things that we want. The initial angular velocity is, of course, 0 because it starts at rest, not rotating. We have alpha, which is given to us at 0.250 radians per second. We have theta, which we just calculated, 1257 radians. And we're solving for omega, so this whole thing is taken to the 1/2 power of the square root. When you plug all those numbers in, you get 25.1 radians per second for the final speed of this train. Oh, sorry, the final angular velocity of the train's wheels. Then we're going to find the velocity of the train, because the relationship between linear velocity and angular velocity is v equals r omega, just like it was up here for distance and angle. V equals r omega gives us 8.77 meters per second, and we're good to go. So, another example. Person using a microwave. Fly flies in the microwave. Poor fly, it's going to die. Why is the fly going to die? Because he has water in his system, and water is the thing that microwaves heat up. But the plate has a radius of 0.15 meters, rotates 6 RPM. Again, we're going to have to convert RPM into radians per second. Calculate the total distance traveled. We're going to do our conversion first. 6 RPM, let's see, goes... Oh, first of all, they're calculating theta in revolutions. They're going to do that, and then they're going to convert. That's fine. Theta equals omega times t. They're using 6 RPM for their omega, and that's fine. It's just the wrong units for plugging into kinematic equations and coming out nicely. But in this case, it works out nicely because they have 2 minutes for their number of time. So rotations per minute times 2 minutes is going to give us rotations or revolutions. So it's going around 12 revolutions apparently. And then we can convert that 12 revolutions by multiplying by 2 pi radians per revolution, and we'll get 75.4 radians of angle for those 12 revolutions. Now we can use the relationship between distance and angle to calculate the distance. You're going to end up with 11 meters of distance that the fly travels, and it will die. Now, dynamics of rotational motion. Of course, we've already talked about torque, which is kind of like the force of angular stuff, but we haven't really talked about it in terms of, for example, Newton's laws. Newton's first law says that there is inertia for things, and that is true for angular things as well, except that the angular inertia, or rotational inertia as we call it, of an object is not only dependent on its mass. For regular inertia, it was only dependent on mass, and the mass essentially was the measure of inertia. But for an object that is rotating, there's one other thing that matters, and that is where the mass is relative to where the thing is rotating, to what point the thing is rotating around. For example, a bicycle wheel has most of its mass outside in this outer edge, and less mass inside here. And so that affects the rotational inertia, or the rotational inertia of the wheel. And what we've got to figure out is, what is it, how does it affect it? How does the placement of the mass, or the distribution of the mass, how does that affect things? Well, if I was in a classroom, I would do some experiments to show you how this works. But it turns out that the further the mass is from the point of revolution, or from the point of rotation, the more inertia it's going to have. And what that means is that it means that if you have more inertia, you resist rotation more. So bike wheels actually resist rotation quite a bit. It's fairly difficult to get a bike moving once you're started. But once it is going, once the wheels are spinning, then they don't want to stop. And that's good for a bike, because you don't want to have to keep working hard to keep the bike wheels turning. If they don't want to stop and they just keep spinning, then it makes your job a little easier. You just have to put a little bit of energy in to counteract some friction and some air resistance. If the mass is further in, if you had a bike tire that was very light on the outsides of the wheels, and all of its mass was more concentrated towards the center here, then you'd be able to get going faster. Well, that's really good for cyclists who want to race, particularly ones who want to sprint. And you'll often see sprinters on bikes, they call them time trial bikes. They actually have very different wheels. So let's take a look at that. Well, this is going to be fun because I have a web protection filter on my home computer for my family. That's not what I want to do. Okay, so let's look at time trial bikes. Yes. And let's look at images of time trial bikes. And you can see here, for example, on this one right here, actually I like this one better because this is my favorite company. We'll go to the other one. I'm actually a cycling nut. This particular time trial bike has wheels where the rims are actually thicker. And a lot of people think, well, that's for air resistance. And it is true that it is more aerodynamic that way, but a big part of that is that the materials of these rims are made of a very lightweight material that needs to be a little bit bigger so that it can handle all the strength, so that it can be strong. But also, another big part of it is that you're bringing more of the mass closer to the center of the wheel. So the rotation of the wheels is actually, so it's actually easier to get the wheels rotating. And that's great for sprinting, because if you want to sprint and get those wheels going faster and faster and faster, you need to have that ease of acceleration. Specialized makes their bikes in conjunction with Ferrari Racing Sports, Ferrari Motorsports. And here's another one. This is an older time trial bike. You can see here that this one has a solid wheel in the back, and that was not uncommon when they first started coming up with these time trial bikes that did for racing these specific sprint races. It's too bad that Lance Armstrong ended up being a doper, because he was so responsible for the increasing cycling popularity in the United States, and now it's just kind of dying off again. But here's another example of this, a newer one, where you have a solid wheel in the back, and part of the reason for that solid wheel is the solid wheel will get spinning faster than the wheel with spokes on it. Also, aerodynamics are part of it, but the rotation is a big deal. So, hey, there's a email from Shay. I will answer that email after I'm done with this. But anyway, this one is actually a different kind of time trial bike. You can see here that it only has one gear and it doesn't have any brakes on it. It's kind of freaky. This is what they use for indoor time trials. Not a sport I would recommend to the people out there who don't like pain. I've known some time trial cyclists, and they are often missing their teeth. When they wreck on the indoor concrete and hardwood tracks, it is not a pleasant sight. They're going about 60 miles an hour, and it's just bad news. But anyway, let's go back to our class here. Excuse me. Hiccup there. So that's rotational inertia, and there's actually a way to calculate it. The way to calculate rotational inertia actually requires some calculus, and so we won't do much calculating of rotational inertia, but we will show you how to do some simple calculations that where the calculus has already been done for us. But let's now talk about Newton's law. If Newton's law were applied to rotational forces, then we'd have to include in an R because force equals mass times acceleration, but linear acceleration is equal to R times angular acceleration. So you would get force equals mass times R times angular acceleration. Well, if you're going to also include torque in this equation, then you would have to multiply the left side by the radius as well to get R times F for the torque. And so then you would get R times F equals M times R squared times alpha, because you'd have to multiply by R on both sides. And then you get an equation that says torque is equal to M times R squared times alpha. Except that this doesn't look nice and clean like other things did, like we had with our kinematic equations, for example. We had to add in an R squared. We had to multiply in an R squared. Well, it turns out what the real equation is in rotational dynamics is not torque equals mr squared alpha. The real relationship is actually this. Torque, net torque, equals I times alpha, where I is the rotational inertia. And the rotational inertia ends up being the mass times the r squared. They show it here. Here they're showing it as the sum of all the masses times the radius squared. And the reason they show this is for the people that are learning calculus out there. But essentially, if you just had a bunch of different masses at different radiuses from the rotational point, you could calculate the total inertia of the system using this equation. Of course, if you're taking calculus, you can recognize right away that this is going to turn into an integral, and you're going to be able to calculate the rotational inertia for any shape of object. But this essentially becomes Newton's law, Newton's second law, for rotational motion. You get the net torque, or the total torque, equals I times alpha. And now we're starting to make connections between linear dynamics and rotational dynamics. The only thing that we have to know is what is the rotational inertia going to be for different objects. In the first one we did, it was essentially just a mass that was going around in an orbit around a circle. And that gave us the mass times the radius of the circle squared for the rotational inertia. But it's not going to be true for everything. It is true for some things, though. For example, if you have a bunch of masses all connected at the same radius around an axis of rotation, like a hoop or a ring around a circular axis, then the rotational inertia is equal to mr squared, just like it was for a single mass. But this is only true if this hoop is really quite thin, or if the ring is really quite skinny as well. However, if you have a solid cylinder or disk that's spinning around its central axis right down the middle of it, it changes things. It's not mr squared, it's actually mr squared divided by 2. And that comes from calculus. However, if you have a rod, like a cylinder, that's not very thick, it's kind of a thin rod, and it can be really any shape, as long as it's quite small on this axis compared to its length, then the calculus turns out to give us a rotational inertia of m, the mass of the rod, times L squared, which is the length of the rod, divided by 12. And that's if the axis is through the middle of the rod like this, and it's swinging around like a baton. Then if you had a solid sphere, any diameter, right? The diameter is 2 times r. Then the rotational inertia ends up being 2 times mass of the cylinder, times r squared over 5. That's for a solid sphere. But if it's a hollow sphere, and the shell of the sphere is quite thin compared to the radius of the sphere, then it's 2 times mass times r squared over 3 instead of over 5. And so on and so forth. You have an equation for a rod about the end of the rod. You have a solid cylinder or disc that's thicker around the center, right? And then you also have one for a ring that has 2 different radiuses. It's a thick ring, and that gives you that one. I mean, you can see that we've given you quite a few. And now we're going to have you do some examples here, calculating the effect of mass distribution on a merry-go-round. Of course, a merry-go-round can be considered like a disc. And so we can go up here and we can say, well, which one is the disc? Well, the disc is going to be, here it is, a solid cylinder or a disc about the cylinder axis or the disc axis. So that's the equation you're going to use for this one. And they give us some information. They tell us the father is pushing the merry-go-round. He exerts a certain force. They tell us the mass of the merry-go-round, the radius of the merry-go-round. We're going to convert this all into angular stuff. The angular, Newton's law is angular acceleration equals net torque over rotational inertia, or we can write it in simpler form without writing the net torque, or we can rewrite it as torque equals angular acceleration times rotational inertia, whatever. But in the end, we need to calculate the torque, we need to calculate the rotational inertia, and we need to figure things out. So calculating the torque, it's r times f times the sine of theta. The father is pushing this thing at a 90-degree angle to the radius, so the sine of theta becomes 1. It's just the radius times the force, 375 Newton meters. The moment of inertia, it's for a solid disk, 1/2 mr squared, so that's I. Now we have both the things we need to calculate the angular acceleration, the torque and the I. We put them in the equation, we get 6.67 radians per second squared. Easy. Now, for part B, they want us to calculate the angular acceleration if we put a child on this thing. Well, what happens if we put a child on this thing? It's just like if you put a mass on a car that you're pushing forward. You add the masses together, but in rotation, you're going to have to add the moments of inertia together. You have the moment of inertia of the child and the moment of inertia of the merry-go-round. So here's the moment of inertia of the child. It's just mr squared because it's just like the child is just like a single mass at some radius. And they give you the information for that. You plug it in. You get the moment of inertia for the child. You add that moment of inertia of the child to the other moment of inertia that we got to get a total moment of inertia for the child plus the merry-go-round. And then you plug that into your Newton's second law, alpha equals torque over moment of inertia. And you get less radians per second squared because the child has been put on there, so it's harder to get it going. That makes perfect sense. Now, 10.4, work and energy. We can convert linear energy into rotational energy, but what is that going to look like? How is that going to work in the mathematics? Well, that's exactly what we work through here. Net work equals net force times distance, change in distance. Well, if our change in distance is rotational instead of linear, how is that relationship? The relationship is you take the linear, the delta S, and you divide by the radius over the rotation. But how does the force change? Well, the force becomes a torque. How does it become a torque? Because we divided by r here, we have to multiply by r here somewhere, so we do it over here, and it becomes a torque. We have an r times a force. So now we have torque times theta instead of force times delta S. And that's the work done to rotate an object through an angle theta with a torque tau. Plain and simple, right? Now, is there going to be an I in here? Is there going to be an I involved? Well, sure, because remember that work is equal to energy, and so we're going to end up with things that are like with the kinetic energy, we got 1/2 mv squared, for example. So I'm expecting that we can get a 1/2 something times something squared. For m, we've been replacing m with I for rotational, so maybe the I will be in m's place. And for v, we had omega, so maybe the omega will be in there. How are we going to figure it out? Well, we just replace our sorry, I'm looking for the place where they show this to us so I can show it to you. Oh, remember that in our last section we had force equals mass times acceleration, converting into torque equals I times alpha, right? And so in this equation we can replace our net torque with I times alpha, so we get work equals I times alpha times theta, which is great because we know what alpha is. Alpha is actually delta omega over delta t, and we'll actually eventually do that down here. Looks like they're doing it a slightly different way. Let's do it their way. So they're doing it a slightly different way. So net work is going to be I times alpha times theta here, and they're going to use actually a kinematics equation here to solve for alpha times theta, because we have an alpha times theta up here. When they solve this for alpha times theta, they get omega squared minus omega naught squared over 2, which happens to give us this equation. The net work done is going to be 1/2 I omega squared minus 1/2 I omega naught squared, which is kinetic energy, 1/2 I omega squared, just like we were saying we might get. So then we say that's what we're going to call rotational kinetic energy, 1/2 I omega squared. And now we have conversion from linear to rotational energy and work. So this next problem does exactly that kind of example. We have a large grindstone. The person spins it by exerting a force on the edge, so it's a linear force which creates a torque, and they're going to do it, push this thing through part of a revolution, and we want to verify the work done by the torque she exerts is equal to the change in rotational energy. So we want to make sure that energy is conserved here, is essentially what we're doing. A, how much work is done if she exerts a force of 200 newtons through a rotation of 1 radian. The force kept perpendicular to the grindstone's radius, so the theta will be 90 and the sine of theta will be 1. Friction is going to be negligible, and then B, they want to find the final angular velocity given the mass, and then C, they want to find the final rotational kinetic energy, right? And the part A and the part C should all be equal if energy is conserved. So first of all, we're going to need to start calculating some things that we have into things that we need, and that includes for this first part, what was the first part? They wanted to know the net work, right? How much work is done if she exerts. So yeah, she's going to exert some work, 200 newtons through 1 rotation. So the net work is going to equal the net torque times the theta. They've given us the theta. We need to calculate the torque. The torque is going to be R times the force. They give us both of those things. We just plug them in here, and we're going to get a torque, we're going to get a net work of 64 Newton meters or 64 joules. That should be equal to the same thing in part C. Then we're going to use a kinematic equation to get the what are we calculating in part B? We're finding omega, right? So here's a kinematic equation that we can use to find omega if we can figure out everything that we know. And it turns out that our initial omega is 0, so this equation becomes omega equals square root 2 times alpha times theta. And 2 times alpha times theta is something we're going to need something else for, and that thing we're going to need is going to be the angular acceleration. So the angular acceleration can be calculated from the net torque over I. Well, okay, the net torque over I, we don't know I, we don't We do know the net torque, however. The net torque was actually calculated 64 Newton. No, it wasn't. Um, that was the work done. So the net torque is going to be the force times the radius. 0.320 meters times 200 newtons gives us 64 Newton meters of net torque. Kind of interesting that that's very similar, but anyway. And then the moment of inertia, right? We need to calculate the moment of inertia. For a disk, it's going to be 1/2 mr squared, it turns out. So we plug in our mass of our disk and the radius, and we get 4.352 kilogram meters squared. For the I, for our rotational inertia. And now we know everything we need to do to calculate the alpha, to calculate the angular acceleration alpha. Plug those numbers in, we get 14.7 radians per second squared. And then we can plug everything back into the kinematic equation and get 5.42 radians per second of angular speed or angular velocity after this has been pushed. This wheel has been pushed. Then, the final rotational kinetic energy, we can use the kinetic energy equation for rotation, 1/2 I omega squared, because we have all that information. Plug in those numbers and we get the same number of joules that we got previously. 64 joules. Problem-solving strategy for rotational energy. Hey, it's the same as the linear one, except you're using different equations now. Same equation, it's the same idea. Same ideas for the kinematics, same ideas for the dynamics. The only thing that's really going to change is we're going to actually have new types of energy we can plug into the equations for conservation of energy, right? Conservation of energy can include initial linear kinetic energy, initial rotational kinetic energy, right? And potential energy can also be considered, well, we're not going to talk about potential energy any differently because that's still going to be spring potential energy or gravitational potential energy or whatever. But the kinetic energy has a new kind of energy that can be involved there, right? It can be rotational kinetic energy as well as linear kinetic energy. So, helicopter engines. Goodness. Seems like it's taking forever, but it's only been 47 minutes. I can't really take a break in the middle unless I just let the recording run, which I might just do because it gets tiring talking to myself here in my living room. Okay, people are going to think I'm crazy. We have a rescue helicopter, 4 blades, 4 meters long, each has a mass of 50 kilograms. When they give us problems like this, we're going to have to start figuring out ways to make a rotational inertia for these things. So 4 small blades are like 4 rods that are rotating around their ends, or 2 rods, well anyway, like 4 rods. And so that's the kind of thing you have to think about. Part A, they want us to calculate kinetic energy. 1/2 I omega squared, we're going to need omega, which we can get from the numbers they give us. But the I, we're going to need 4 times ml squared over 3. ml squared over 3 is the formula for calculating a rod that's rotating about its end. And so we use that and we get the I, and then we can just calculate rotational kinetic energy. Translational kinetic energy, of course, is going to be 1/2 mv squared, and we have that as well. And then to compare the kinetic energies, you take translational to rotational, and you get 0.380. So the rotational kinetic energy is actually less than the translational kinetic energy. And then at a maximum height, all the rotational kinetic energy is converted into gravitational energy. So you can actually calculate how high this thing can go if you know how fast it can go, how fast it can turn. So that's kind of interesting. So, here's an interesting race. I do a similar thing to this in my classroom. We have 3 cans of soup, and each can of soup has a different density to it, a different mass to it, and they're rolled down. They're rolled down a ramp here, right? And they have a thin soup and a thick soup or whatever. Sorry, I'm saying this wrong. All of them have the same mass. One of them is thin soup, one of them is kind of medium thinness soup, and one of them is thick soup. And they say which one should come down, the fastest or the slowest, whatever. We'll get back to that in a second. I'm going to take a break. I need to get a drink and walk around a little bit. But I want to take a break. I'm going to leave the recording on. I'll be back in just a few minutes. Okay, we're back. We're ready to go. Oh, we're talking about soups and I don't want to do this. We gotta move on before I fall asleep here. I'm getting tired. So actually, they go ahead and explain this little experiment done here, and that's fine. And it has to do with energy being stolen away by friction inside of the soup can. The thicker soups being more viscous and more frictiony. But anyway. Calculating the speed of a cylinder rolling down an incline. So we have a cylinder rolling down an incline. This is where it gets kind of interesting because, of course, at the top of the incline, the cylinder has potential energy, but as it rolls down the incline, the potential energy doesn't just turn into kinetic energy of it moving forward, but also kinetic energy to rotate the can. So your conservation of energy looks like this. Potential energy initial, mgh, equals 1/2 mv squared. That's how fast the can is moving forward. Plus, in other words, this is a tangential velocity along the edge of the can, right? Plus 1/2 I omega squared, which is the rotational velocity, rotational kinetic energy of the can, right? And so, in this particular case, it's actually a good idea to convert everything into either linear or angular terms, depending on what they've given you in the problem. In this case, they've given us linear things and linear values, and so or we're actually trying to calculate a linear value too, so that helps as well. But anyway, we go ahead and turn everything into linear values, and that means really that we need to turn our I into 1/2 mr squared for a rolling cylinder, which is rolling around its central axis, and then the v squared over r squared, which is the omega squared. And then we can actually notice that there's a mass in each one of these terms. Get rid of it. And then we can actually solve for v. And this is the v that we get in the end. V equals 4gh over 3 to the 1/2 power. Plug in our numbers, we get 5.11 meters per second. And the question is, would this be slower or faster speed if the incline had no friction and the can just slid down it? It turns out that this is slower. Rolling down an incline actually is slower than sliding down an incline, which, of course, anyone who's gone sledding knows. Sledding is fun because it's fast, and you slide down the incline. Of course, you can get going fast when you're rolling, but it takes longer to get going, and you never get quite going quite as fast at the bottom. So 10.5, angular momentum now. So we've gone through kinematics to dynamics to energy, now, of course, momentum. Well, why even try to figure it out? If linear momentum, P, was equal to mass times velocity, then angular momentum, which we're going to call L, is going to be I times omega, because I replaces mass and we replace the V with the omega. Plain and simple. We're just going to say it is so. And it turns out that it is. And it also turns out that angular momentum is conserved. So here is an example, 10.11. We're going to calculate the angular momentum of the Earth. The Earth is like a big solid sphere, so it's going to be 2 mr squared over 5. We can get the r and the m from the book in the index, not index, but in one of the, anyway, somewhere in the book, or you can look online. But they also just give it to us here, so we're good to go. Then the omega we can figure out on our own as well, because it's 1 revolution per day, 2 pi radians per day. We need to turn that into radians per second, not that hard to do. And then you just plug it all in. Once you've plugged it all in, you get an angular momentum of 7.07 times 10 to the 33 kilogram meters squared per second. Pretty big number. This is actually the reason that the Earth has continued spinning. This is why the Earth continues to spin. Some people like to think that it's because of something in the core of the Earth. No. The core of the Earth is also spinning, but it's spinning just for the same reason the Earth is spinning. At some point during the formation of our solar system, there were things that were orbiting around the sun, and they, chunks of rock and ice and iron and other things. And as they collided with each other, they collided each other slightly off kilter, and that off kilter colliding caused the masses to rotate. And as they collided and stuck together, they became a rotating mass of junk, space junk. And then eventually it got bigger and bigger and bigger as more things hit it, and more things hit it at funky angles and caused it to rotate more and more and more and more. And eventually we got the rotation that we're stuck with today, and it doesn't change because it's so huge. It has such an incredibly huge angular momentum. Does that mean it could not change? It's possible, not likely, that the Earth's rotation could be changed, but it would require an outside force, like a very big comet or asteroid that would come in and hit the Earth in such a way that it actually gave the Earth momentum in the other direction, right? It would have to be so big that it would kill everybody and everything on Earth. And so we would never be able to measure the angular momentum of the Earth after that. In fact, even if we were on the space station, we would be destroyed. So not likely to ever happen. Well, not likely we'd ever measure it if it did happen. And if it was about to happen, we could do nothing to stop it. Okay. So we're doing angular momentum into a lazy Susan in this problem. A food tray is being rotated. Suppose they exert a 2.5 Newton force, 0.260 meter radius for 0.150 seconds. What's the final angular momentum if it starts from rest? Assuming negligible friction. Okay, so we have our angular momentum equation, L equals I omega. We need to know both of those things. But it turns out that we also are going to have a similar thing to impulse. And I didn't mention that up here, but they do talk about it right here. In the linear momentum section, we had impulse, which was equal to force times t, which is this equation here, delta p over delta t, but it was rearranged. So the impulse was change in momentum of force times delta t. Well, to make that an angular thing, we call it torque times delta t equals change in L. And so we get this equation here when we solve for the net torque. And of course the net torque is something we can calculate because we have the force and the radius. Once we calculate that net torque, we'll know how much change there is over time in the momentum, and we can use that to calculate our momentum. And that's exactly what they do. They end up with delta L equals net torque times delta t. Plug in their force, their R, their delta t. They get the L, that is that final angular momentum. The final angular momentum is also, however, equal to I omega, and they want to know the angular velocity, so we need to calculate I to get that. They're going to use for this food tray a disk, I believe, 1/2 mr squared for I, so they're using the formula for a disk. And then they plug that in and they get 0.721 radians per second for their final angular velocity. Calculating the torque in a kick, of course, you're going to have a swinging leg, you're going to have a radius, you're going to have the speed of the foot, or angular velocity or something. They're giving us mass. Also, moment of inertia of the lower leg. They actually just give us the moment of the inertia. They don't even make us calculate that. They give us the length of the lever arm, 2.2 centimeters. Turns out they want to find the angular acceleration of the leg and the rotational kinetic energy of the leg after it's rotated through 57.3 degrees, or 1 radian approximately. And so we just start, figuring out things and using equations that will give us the things we want to know from the things we already do know. And the first, in part A, they're asking for the angular acceleration of the leg. Well, we know that torque is equal to I times angular acceleration. But also we know that torque equals R times F. So if we calculate the R times F and we get the torque, then we can plug it back into this equation and divide by the I of the leg to get angular acceleration, which is exactly what they do. For part B, we can calculate the final angular acceleration because now we know the final angular velocity, because we know the angular acceleration, and we know the theta that it's going to rotate through, which is about 1 radian. So we plug in those numbers into an angular motion kinematic equation. And for the last part, rotational kinetic energy can just be calculated because we know I and we know omega now. We just plug them in and we're good to go. So we're not learning anything really new. We're just learning how to apply what we already know in a new situation. Right? And here's where they do the angular momentum of a spinning skater. They start with their arms out, which actually gives them a different I than with their arms in. With their arms out, their mass is further from the center of their body, so their I is bigger. With their arms in, their I is smaller. Since the L has to be the same in both of these equations, and the I is big over here, then the omega is small. But when the I becomes small, the omega comes big, and they spin super fast. And they do an example of that. They actually use kinetic energy in this somehow too. What do they give us in this? They give us the speed and the rotational velocity here. They give us moment of inertia, arms extended, moment of inertia, arms close in. They want to know the angular velocity and revolutions after she pulls in her arms, and the rotational kinetic energy before and after she does this. So they just write this down because we're going to use it later to calculate rotational kinetic energy. But they actually use the conservation of angular momentum to calculate the final angular momentum. I omega equals I prime omega prime. And we know everything except omega prime, given it to us. And so we find out we do have to do a conversion in there because they have revolutions per second. So once we get revolutions per second, we're going to have to calculate radians per second. They do that later. 2 pi radians per revolution gives that conversion. And then they calculate the rotational kinetic energy before and after, and good to go. If you notice here, on the end of this example, the rotational kinetic energy before she pulls her arms in is 29.6. After, it's 191. So again, kinetic energy, rotational kinetic energy is not conserved. Just like with some collisions we saw, particularly non-elastic collisions. So here they show the formation of a solar system where you have just a bunch of mass rotating around in kind of a disk, and as gravity pulls it towards the center, you get a big ball of it in the center, and then other pieces start to collide together and coalesce together, and you get planets going around and around and around. And this is why the planets go around and around and around the sun. It started off with a rotation. But where did the rotation come from? Well, that's a really good question. The rotation came from, and this is actually the basis for this theory, some kind of explosion that happened that created an acceleration, and part of that acceleration resulted in eddies, in little swirly currents out in the universe. And those swirly currents turned into galaxies that go around and around, but it also turned into solar systems within galaxies that turn around and around, and stars that turn around and around, because stars do rotate as well, and black holes that turn around and around. I mean, some stars move super fast around and around. They're called quasars. And so there's lots of things rotating in the universe, and that came from some kind of big explosion at the beginning. Where did that come from? Why was that the case? We don't know, but we do suspect that it had to be from some big expansion of energy. So we call it the Big Bang, and there's theories about how the Big Bang started and everything else, but we haven't really been able to verify those yet. So now let's look at collisions. Of course, in one chapter we're going through all previous 7 chapters essentially. This is chapter 10, which was previous 9 chapters. I guess that's right. So anyway, I keep saying in chapter 8, but that's because I was doing homework from chapter 8. But anyway, collisions is the next thing. We're going to cover all the first however many chapters, first whatever chapters it were. We're going to do it all in one chapter. It's exciting. So we have a linear motion, which in this case looks like a disk, frictionless surface, and then it's going to hit the end of this ruler that is nailed down, and it's going to make it rotate. And afterwards the disk may still be going, and the little ruler is going to be spinning, or maybe the disk could stop even and the ruler could be spinning or something else. But there's going to be a transfer of energy, momentum, and so on and so forth. So in this first example, they want us to calculate the angular velocity of the two after the collision, kinetic energy before and after the collision, and the total linear momentum before and after the collision. They give us the mass of the disk, the initial velocity, and the stick 1.20 meters long, and the mass of the stick as well. Well, conservation of momentum is an effect. So conservation of momentum says that the initial angular momentum equals the final angular momentum. The problem here is that how do you calculate the angular momentum of a disk that's moving in a straight line? Well, it turns out that if you can find the initial momentum and the final momentum, angular momentum that is, and then take the difference between the two, then you're good to go. It's not really rotating, but you can calculate the initial and final angular momentum. So how do we do that? Oh, actually, I'm doing a different problem than this all of a sudden. Okay, so how do we find the angular momentum of the disk? That's slightly different, actually, because, as I was just reading through this example, the next part, I realized my mistake. I was actually doing a problem that we will probably do later of a plane flying through the air and having an angular momentum that changes. But in this case, all we really care about is the initial angular momentum of the system, not the change of angular momentum of the disk as it flies by. And that is absolutely true, because what we're really interested in is the angular momentum of the disk just as it's about to strike the ruler, or the whatever, the stick, because that is where all the momentum will be in the disk at that point. And so what we can do is we can consider, or we can suppose, that the disk is like it's kind of like on the edge of a string that could rotate around the center of rotation that the stick is going to rotate around, because it's hitting it right at the end of that stick, and so it's kind of like at that same radius. And so we do that, and it is an approximation, but it's a very good one, actually. And so the angular momentum of a ball at the end of a string is going to be I times omega, and the I is going to be mr squared, because it's just a single item going around in a circle, right? And then omega is, of course, going to be v over r, and we get this equation here. And you can see here that one of the r's is going to cancel out, and we're going to get just mvr for that ball, or for that disk that's sliding along. That's our initial angular momentum. Afterwards, however, we're going to have two things going on. We're going to have the disk starting to rotate, and the ball, not the disk, the stick starting to rotate, and the disk will be moving at a different speed, and so we'll have a different angular momentum relative to that center of rotation. So angular momentum says that these two things have to be equal. To find the final angular speed, we solve these two things, and the only thing we need to know for this equation now is this I prime after these things have hit. Oh, it actually says that they stuck together. Did it say that earlier? It doesn't. Okay, so they're assuming that the disk, they're going to assume the stick and the disk stick together, which is a good assumption just for the moment just after they've hit each other. So that's why they're assuming that. They don't know that they really say that, but just right as the disk is hitting the stick, you can assume that they become one mass. And so this is where we're going to calculate the I, where we take the rotational inertia of the ball at the end of the disk, m times r squared, plus, the disk at the end of the stick, plus the angular inertia of the rotational inertia of the stick, which, if you look up in the table for shapes of a stick rotating around its end, is mr squared over 3. Then we go ahead and we simplify this if you want to, so that you get the masses added together times the r squared. And that becomes our I prime, which we plug into this equation, and then we're done. I mean, at that point, we've got everything we know. We plug everything we need to know. We plug it in, and we get the answer for part A. To get part B, we calculate linear kinetic energy for the disk at the beginning, K equals 1/2 mv squared, and then rotational kinetic energy at the end for both things, which we have the I prime and the omega prime for already. And you can see that at the beginning we have 22.5 joules, but at the end we have 1.57 joules. It takes a lot of energy to get things rotating, apparently. And that energy is essentially not conserved once again. Then part C, we want to calculate linear momentum and angular momentum. So linear momentum of the disk, just mass times velocity, and then angular momentum at the end. No, linear momentum at the end, rather. They want to do linear momentum at the end. So linear momentum at the end is going to be mass times velocity for the disk, mass times velocity of the center of mass for the stick, and it turns out that that's just going to be mass times velocity of the stick divided by 2. And then we get we start simplifying, and we replace our v prime with r omega prime, because that's the relationship between linear and rotational once again. And then we've got everything we need to know. We plug in, we get 2.2 kilogram meters per second for our final angular velocity. So initial angular velocity 1.5, initial angular momentum 1.5, final, I still said it wrong. Initial linear momentum 1.5, final linear momentum 2.2. So you can see here that linear momentum is actually not conserved. And so when we study angular momentum, we actually learn something new. It's not momentum that is conserved. It's very specifically angular momentum that is conserved. In general, momentum is not conserved. In general, linear momentum is only conserved if you're moving in straight lines. If you're moving in 2 dimensions or 3 dimensions, but moving only in straight lines, then linear momentum is conserved. But if you turn, if you rotate, if you orbit, anything like that, if you change from straight motion to turning motion, momentum is no longer conserved there. Only angular momentum is. And that was huge discovery that happened actually fairly early in the study of physics. And when we finally got onto modern physics later on, we immediately assumed that for everything. And it led us to some great discoveries. Here they're actually talking about the sweet spot of a tennis racket, the sweet spot of baseball bats are very similar, and how those things can be calculated. Of course, those things are calculated. Sports these days do not just do things by feel or by instinct anymore. And it's one of the things that I truly believe in for the success of future sports. I think that coaches and even players should be scientists. They shouldn't just be athletes that were really good athletes and they had a great instinct for the game. That worked. That was a really great thing, all the way up until about 20 years ago. But 20 years ago, coaches started coming into the scene that had never been good players and sometimes had never played the sport at all. And what was the difference? The difference was that they studied the sport from a scientific point of view, and they were able to detach themselves from their quote-unquote instinct, and they were able to make decisions based on science. And that has revolutionized sports. Instead of making a decision that says, well, I just think that's the right thing to do for this player and that for the other thing, and completely destroying the game, sometimes destroying the player's body or destroying something else because their instinct was just not quite right, they can make a scientific decision which has a much better chance of having the best result. Does it always have the best result? No, because scientific decisions are not going to have that luck factor involved. They are going to work the majority of the time, though. They're going to have the best overall chance for success in the long run. And so you see teams all the time now that have great moments but can never quite finish the season off. And they can never quite, win regularly. And it's kind of funny. I mean, it's funny to me because one of my favorite teams is using this to their advantage. The San Francisco Giants have decided that they're not all about big names and big money players. They're going to play the game scientifically. And last year, they were not picked. Last year, they were not picked to win the World Series. They were picked to finish well. And at the end of the season, they didn't win the They didn't win the first place in the National League tournament. They were actually put into the tournament as a wild card, and they had to win a last minute game with another team, even to get the wild card berth. So they were put in there as kind of the team that gets to be in there because they were almost good enough. And then at the end of the season, they just went on this run that was just crazy. They could not be beaten. But why was that? Because they weren't worried about wins and losses during the season. They weren't worried about making their mark on the season. All that they were worried about was preparing their players and preparing their season so that at the end of their season they're at their peak performance. And people think they're crazy. But it's true. It's true in every sport. Sometimes the season has the least amount of bearing except that it's preparing you for the end of the season. And I've tried to get that through many coaches' heads, particularly traditional coaches and people that are taught by traditional coaches, but their brains are just not ready for it because they've never learned science, honestly. And if you don't learn, and it's different than just learning mathematics, you have to learn science because this stuff is applied mathematics. It is extremely much more complicated than mathematics. And if you can learn it, you can apply it. If you can apply it, you can change the way you're doing things. And sports is a great example of where science is changing kind of everyday lives and people don't even know it. Of course, that happens all the time. Okay, so the very, very last thing that we're studying this time is gyroscopic effects. And in this one, we're essentially going to be equating force and angular momentum, similar ways that we did linear momentum and impulse and force and everything else like that. However, what we're going to talk about in this particular case is angular momentum and torque as vectors, not just about counterclockwise and clockwise, but the actual way that they're talked about as vectors. And this involves a strange thing that we call the right-hand rule. With the right-hand rule, you take your right hand and you curl the fingers in the direction of the rotation of the object. So in this case, if we have a disc that's rotating counterclockwise, you rotate your fingers counterclockwise around the disc. And then you stick your thumb out, and the thumb will tell you the direction of the angular momentum. Will also tell you the direction of the angular velocity. It'll also tell you the direction of the torque that was required to get this thing turning in that direction in the first place. It tells you a lot of things. So the torque, angular momentum, the angular velocity, all of them are actually pointing not in the direction of the rotation at all, but 90 degrees to it. The reason that we don't talk about this very much in this algebra-based course is because understanding how the vector math works with this is beyond the scope of this class. It is something you do need to study some more advanced math for, particularly some calculus and what we call linear algebra. But it's not terribly difficult to learn it in the basics. So we teach you the right-hand rule for things that are rotating to figure out directions. Why would we want to know that? Because if that is the direction of the angular momentum, then that direction also has to be conserved in conservation of angular momentum. And gyroscopes are things that demonstrate that conservation quite well, even though it's not very intuitive. It's very difficult to understand this stuff, to make sense of it, but it does explain it. So the classic example of this is the gyroscopic bicycle wheel. And I wish I had enough of these to give to everyone to take home, but I don't. I should have sent a gyroscope with you, Shannon, but maybe I'll come down and bring one to you. I'll just bring my bicycle wheel down when I come in. But anyway, you start with this bicycle wheel, which you're holding, and you spin the thing. And in this case, they're going to spin. Where are they going to? Oh, they're going to spin the wheel so that they grab the top of the wheel and they pull it down in front here, so that this wheel is going up on the inward side towards the person, and at the top it's going away from her and down on the outside part. And that means that the angular momentum of this wheel, if we put our hand around the wheel this way, our thumb will be pointing out this direction, this pink direction here, and the angular momentum is to this lady's left. That angular momentum both its strength and its direction has to be conserved. So what will happen to her if she tries to turn the wheel, if she tries to rotate the wheel to a different direction, for example? And that's the fun part. What I like to do in my class is sit this person in a chair that rotates, and I have them turn the wheel, and they have to figure out which way the chair is going to rotate and why. Well, it turns out that the chair is going to rotate in a way that is going to restore the angular momentum that was changed when you tried to turn the wheel. So here is my original angular momentum, L, L, this pink one down here. And she's going to rotate the wheel. It looks like she's going to lift it with her right hand and push down with her left hand. So she's going to rotate the wheel so that this side goes downward and this side goes upward. Well, that's going to make a, let's see, we're actually showing, that's essentially going to cause a change in L that is going to be downward, because the new L of the wheel is going to be at an angle down here. I don't really like the way they're showing this picture, but it's going to have a delta L that is downward here, kind of pointing down the axis, the long axis of her body. In order for this wheel to conserve, in order for this system to conserve the angular momentum, if she's sitting in the chair, something is going to have to happen that's going to counteract that delta L. In other words, it's going to have to have a delta L that's pointing up instead of down. Well, what is going to have a delta L pointing up? We use a right-hand rule and we put our thumb up and we look at which direction our hand is turning, and it turns out our hand is turning such that there would be like a circle around her body that if you were looking down at it would be going counterclockwise around, like around her hips or something. Well, in the chair that she's sitting, what will happen as she tries to push that wheel down on the left side and up on the right side is the wheel will start rotating counterclockwise as you look down on it. And the chair actually conserves the angular momentum. And it's a fantastic demonstration. Gyroscopes do the same thing by just tilting themselves, and if you try to tilt them out of their way, then they rotate to account for that change in angular momentum. And that's how gyroscopes are used in navigation. Ships and submarines and planes have gyroscopes on board that are constantly spinning because motors are spinning them, and they're a mass kind of like this gyroscope here. And so you've got this you've got this mass that's connected to this rod here that's spinning really, really fast. And this golden thing out here is just a cage to hold it together. And you get this thing spinning really, really fast, and the ones on airplanes are being spun by motors all the time. And then you just point this thing in the direction of north. And anytime the plane turns, this thing keeps spinning the same direction. It always tells you where north is. And if you make a turn really quickly, it will actually make this thing kind of bob a little bit, and the direction that it bobs can tell you which way you've turned, actually, which is really interesting, because now this doesn't only act as a compass, but it also acts as an accelerometer. It tells you which way you've just turned and how quickly you've turned. How much it deflects depends on how quickly you've turned. So it's a great tool, and they've actually figured out ways to make these out of lasers, where lasers go around and around and around a circle. And you say, well, wait a second, laser light doesn't have mass, so how can it have an angular momentum? Well, it turns out that you don't necessarily need to have mass to have angular momentum, and that's an interesting question for the second semester. And that ends this lecture. It wasn't 2.5 hours long. How about that? Apparently I talk fast when I'm not talking to my students, when I'm not in the same room with my students anyway. So anyway, I'm going to be off to scout camp probably when you guys watch this. If you have any questions, feel free to email me. I will have a cell phone. I can't remember which cell phone number I'm going to have, but I will email that to you when I get it. But I should have connection on my iPad, and I should be able to communicate with you by email and send EduCreations videos and whatever else that way. Have a great week. We'll see you later.